insane how many apples he goes through. And I'm live. Yeah, it depends on what type of apple. No, it depends on what type of apple. Because if you're talking like Granny Smith apples, like I'm not a huge fan of Granny Smith, but my son is. He loves things that have like strong tastes. You know? Are you sure? Ooh, I guarantee you that if I asked everybody to turn against you, they'd do it in a moment.
What are you promising?
Nothing. Yeah.
Mr. Marquis, respect.
See, here's the thing you got to realize. At any given point in the school year, I literally have this kind of like effect on people where I could just be like, hey guys, do this thing, and they will absolutely do it. Now, I'm not saying to do this. No. I would say, hey guys, no, don't do this. But if I said, hey everybody, take out several pieces of paper, crumble them up, and throw them at him as hard as you can. Yeah, you see what I'm saying? Yeah.
He just has like that trustworthy like character. It's like, all right, I think I'll do it. Maybe say it's very easy.
You never know. Anyway, so as for today, obviously I'm not going to see you guys for a couple weeks. I wanted to confirm for you the answers to those Enigma problems. I wanted to introduce a small thing that is eventually going to have larger ramifications when we come back. And then with whatever time we have left at the end, I wanted to see how much farther we can get through that website. I got a few levels farther.
How far did you get?
Like level 12. Yeah. See, the one where you guys figured out the word decade, I understand why the answer was decade, but I didn't like get how you got that answer.
I don't remember.
Yeah, but it was decade. It definitely was. But we'll talk. Yeah.
You just had to plug it in and then
Plug what in?
you put the image into Pixar.
Yeah.
And if you go to the draw tool, you know the little dropper thing?
Okay.
Click on that, you can pull a color.
You can pull a color.
Yes. And you can write with that color, but it shows you the hex number.
Okay, and then the first letter of each hex number. Got it.
It's not the first letter, they're all just one letter. I don't know how hex numbers work, but they do.
I get what you're saying, though. I totally get what you're saying. Yeah, maybe I'll look into that. But anyway, first part of this class period, I just wanted to confirm for you the answers to that Enigma last batch of problems that I gave you. For those of you in the chat, if you would leave a comment, that'd be absolutely fantastic. You also have that turning grill mini project thing due today. I made that video for y'all. Okay, no one watched it. There you go. Okay.
Alright,
Yeah.
I tried to turn it in school yesterday, but guess what? Chromebook suck and you can't upload things from your files on a Google Classroom.
Oh,
Yeah.
my bad.
I took pictures. No, it's not your fault. It's school.
Okay. Well, let me confirm some of these answers for you. So again, just make sure we have them correct, starting with Enigma number 8. Enigma 8, the answer was the philosopher of the Arabs. Enigma 9, this one obviously was a bit lengthier in word. It was a Caesar shift cipher. Hopefully that website helped out immensely, with turning that thing around with the Caesar shift. But it should have been the enigmatic person lived during the 9th century. The enigmatic person lived during the 9th century. Yeah. Number 10 was the repeat. Number 10 repeated one of the previous clues, the theory of parallels, or just theory of parallels. Pigment cipher is nice. It's fun. It's like if nobody knows what it is and they just kind of look at it, they're like, what the heck? But I don't know. It's just one of those things. Yeah. Then number 11, that was the one that we went over together as a group because that one was just a bit like, what the heck? But that was the one where we eventually figured out, and I'll write this on the board just for the proper spelling. It was Al, Joff, Libya, and Baghdad, Iraq. If I can spell Iraq today, there we go. Now, what we messed up was that we actually converted the B and the D. It was supposed to be B800, meaning he was born in the year 800, and D for died in the year 873. So that makes a bit more sense. Now we know that it was AD. Yeah, not to mention, we should have figured this out based on Enigma 9. Enigma 9, he lived during the 9th century. These are years during the 9th century. So, one of those little things. Then finally, number 12, frequency analysis. This one was interesting because obviously it took you back a little bit. There are certain things you could have done to kind of guess certain letters at the very beginning. For example, there was like a singular U that you could have guessed was the word A, or the letter A, I should say, something along those lines. And then from there was ways of extrapolating the rest of it. But here's the final actual statement that should have happened. And I'm going to say this a couple times, and I'll say it a little slowly. For Enigma 12, the enigmatic character was a clever man indeed. He studied a lot of subjects, including mathematics. I thought it was going to be like a rhyme or a limerick, but it wasn't, and I was sad. You ever read limericks? Were they like, never, whatever. The enigmatic character was a clever man indeed. He studied a lot of subjects, including mathematics. So obviously, based on that, if you're going to be submitting that late, because now it's late, but if you're going to be submitting that late, I would like the full alphabet for the cipher. That would be fantastic. Excellent. Okay. So I do see the 3 comments in the chat so far. 3 people live watching. Fantastic. Just want to make sure we get this thing going. Okay. So here's what I got to introduce to you. I've talked about this a little bit in the past, but I've talked about the concept of Alice and Bob. Alice and Bob are 2 imaginary figures in the world of cryptology. Alice and Bob, representing A and B, are sending each other messages, A to B or B to A. But every time they send a message, Eve is eavesdropping. Ha 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 ha. I got you. Now, sorry, I was reading the comments on the chat. Eve is eavesdropping. Now, again, these are just like basic names that they've used over the years, just in terms of theoretical situations. Like, okay, Alice wants to send a message to Bob. She wants it to be secure, but Eve is eavesdropping. Let's just say that Eve is able to intercept every message that is going across. How are we able to keep things secure? To say again? Maybe. We'll see. Now, a lot of theories have been thrown around as to how to keep messages like secure. Obviously, we've seen a lot of different examples of ways to encrypt things, whether it be through substitution or transposition or steganography or whatnot. Lots of different really fun, weird examples. Lots of really intricate, terrible examples. But eventually in the 1960s and 1970s, there was a method developed known as public key encryption. Now, I'm not going to go into the details of public key encryption, but just think about that wording, public key. When I say public key, what does it really mean to you? What does that mean, though? What consequences does that have? Everyone has the key, yes. Everyone has the key. No, I'm being serious. When you send an email to someone, that email is encrypted, but it's encrypted using that person's public key. It's basically saying, hey, if you guys want to email me, here is my public key. Now, my public key is attached to my email address. So if you want to email me, jmarkey@barnegatschools.com, you type that in, and then basically the email takes care of the encryption process. But here's the thing, when you encrypt it, you can't decrypt it. And no one has the right key to decrypt it. Public key can only encrypt in one direction. It doesn't work backwards. Right? That's weird, but that's the way that actually works. It only works going in one direction, where it encrypts it, and then boom, it's sent off to me. And then I get it. Now, how in the world am I supposed to decrypt this situation? Well, I have a private key. I use that private key on the encrypted data, and it decrypts it so that I can read it. Public key, private key encryption. For years, mathematicians and cryptologists and linguists and all these people were trying to figure out ways. They figured, okay, this is a theory. Is it possible that we could do such a thing? And eventually, in the 1970s, several independent methods actually figured it out. So remember, we were talking about the Enigma machine and World War II. People didn't know about that for decades. Alan Turing is not credited with inventing the first computer because all of that stuff was classified for decades and nobody knew that he did it. British intelligence, same thing happened with this public-private key encryption. They figured it out in the 60s, but they couldn't say anything because it was under classified documents within British intelligence. And eventually, it was 3 guys from a college in California that came up with a system that they now call RSA cryptology. RSA, created back in the 70s, is one of the most secure cryptographic systems out there. It's insane. It's simple, but it's insane. Now, I'm not here to explain to you exactly what it is today, but I wanted to teach you a major aspect as to how we use it. One of the key mathematical concepts in this type of electronic cryptology is called modular arithmetic. Anyone ever heard that word modular arithmetic? You have? What do you think it is?
I'm not sure if it's math that you can move around.
You can kind of move around. You think modular, I know. Let me give you an example, because here's the deal. Believe it or not, you use modular arithmetic every day. Every day. What time is it right now? It's 8:38. Okay, it's 8:38. Let's round it to 8:30. Let's just round it to 8:30, okay? It's 8:30. What time will it be in 6 hours? So 8:30, which is really like 8.5, I'm going to put 8.5. I said plus 6 hours. And you said to be what? That doesn't make sense. What the heck's going on there? Interesting. This is technically modular arithmetic. In reality, this number, I put this up here, you should really say what, 14.5? And he just said subtract the 12. Yeah, if you subtract the 12, you get 2.5. This is modular arithmetic. I'm going to show you the details of it today. Believe it or not, you use it every single day. But the general concepts of modular arithmetic are so intertwined with cryptology nowadays, it's insane. In fact, a lot of the theories, this is actually really messed up. A lot of mathematical theories have no purpose. No, I did not tell you that math doesn't matter. No, I'm not even saying most math doesn't matter. No, you got to listen to the full story, though. You got to listen to the story, though. There are several ways of looking at mathematics. You can look at mathematics as a means to an end, a ways of applying it to life, or you can look at mathematics as an art form and something that deserves recognition for the beauty that it is. There's two ways of looking at it. People look at prime numbers and modular arithmetic and all this stuff that I'm kind of spouting out, and they look at it as, what's the point? There's no point to it. But there are people who study this subject because they just absolutely love the fact that it actually works. And it's beautiful and it's amazing. And they don't care whether or not that has any real life application. Back in the 1600s, there was a mathematician by the name of Pierre de Fermat. Fermat is most famous for Fermat's last theorem, which is a story unto itself. Maybe I'll tell you that too. I'll tell you the full story. So Fermat, he had this mathematical textbook on Diophantine equations, and he would read through the textbook and he would make certain theorems and certain assumptions in mathematics. But the thing is, he would write all of his theorems in the margin of the page, right? And people discovered it, like after he died, they discovered books and books and books where the margins were just filled with all of these mathematical theorems. But every single mathematical theorem that he wrote down, he did not prove it. He was just like, oh, I have a proof for this. But the margin's too small to fit it. Yeah.
That seems infuriating to read.
It is.
Just in a much.
So in the centuries after he died, mathematicians made it their goal to prove every single theorem that he had written into the book. And there was one called Fermat's last theorem. It was the last one in the book that was never proved. It took until 1993 for it to be proved by a Princeton professor by the name of Andrew Wiles. I read a book about it. It's called Fermat's Last Enigma.
So were they all proved?
Yes.
All right. So basically, did he say he had a proof for him?
Yes.
And he just wrote them down?
He's like, I don't have enough space in the book for it.
He was like, so bad for someone, he's just like,
I know. So now here's the cool thing. Not the last theorem, but one of the theorems that Fermat came up with had to deal with modular arithmetic and prime numbers. And again, it's one of those things where it's just like, there's no point to this. What's the point for this? He came up with this theorem back in the 1600s. It wasn't until the 1970s that these three guys from California looked at that and applied Fermat's modular arithmetic prime theorem to cryptology and was able to create the security that you now enjoy today on the internet.
and James Markey was one of them.
Right, I'm sure. But I'm just saying, a theorem created in the 1600s applied to computer programming in the 1970s that allows you to go on Amazon and buy something without somebody stealing your credit card information. Isn't that messed up?
I don't know what messed up, but that's pretty sick.
Yeah. Pretty. So, if you would, I'm going to need those notebooks out and open. Is it?
Yeah, people don't know that.
See, it's impossible to think that they're, oh, well, you know what? Ignorance is bliss. I don't know it, and I don't know that I don't know it, so who cares? But at the same time, I think it's pretty logical to think at no point will I ever know everything. Is that fair?
Yeah.
So there are some things that I don't know.
Yeah.
So I know that I don't know things. Well, no. That's not ignorance. It's not even acceptance. It's just realizing where you stand in the world.
A realization. Bro, I'm becoming immortal for Mr. Markey wrong.
I'm going to outlive all of you.
You can say that. I mean, you did say you wanted to.
One way or another, I'm going to outlive all of you.
Well, you just have to become the oldest person in the world at one point. You gotta kill off everyone older than you.
That was a threat. I said one way or another. Anyway, so I want to explain to you the details of what modular arithmetic actually is. There's certain notation that we can use. Well, let's just see what happens. I can say, for example, that, let me do this. I'll do this one. 13 is the equivalent of 1 mod 12. Now notice I didn't do an equal sign. I did this like kind of like a triple equal sign. Oh, it's focusing. There it goes. It's kind of the notation that we use for modular arithmetic. I mean, people kind of go in and out of it. It's not like a hard and fast rule. Like you have to have the 3 line. No, But 13 is equal to 1 mod 12. And you can think of it in 2 ways. What is 1 o'clock in the afternoon army time? 1300 hours, right? Yeah. 13 minus 12, as you said, gives you 1. One way of looking at modular arithmetic is by that subtraction rule that you were talking about, where you would subtract off whatever the modular is until you get a number that is small enough where you can't go any farther. You can't go into the negative realm or 0. Well, technically you could go 0, but we'll talk about that. But in reality, the reason why 13 is equal to 1 mod 12 is because 13 divided by 12 is equal to 1 remainder 1. It all has to do with that remainder. It all has to do with that remainder. I forgot to get into the chat. I meant to do that on my phone here just in case people had questions. So I'll make sure I flip the thing around. Give me a number that's not 13, but greater than 13. Oh my gosh, you guys are lame. 14 divided by 12 is equal to 1 remainder 2. Is that fair? So then I can say that 14 is the equivalent of 2 mod 12. The number that it is equivalent to comes down to the remainder that you get after dividing by the modular. It's kind of a weirdish type of system. So I'm going to do something with mod 4 real quick. Give me a 2-digit number to start at.
25.
Okay, we'll start at 25. 25, 26, 27. I don't know why I almost did that. 28, 29, 30. Now I'm going to do mod 4 here. 25 divided by 4. What's the remainder?
1.
Yeah. The remainder is 1 mod 4 because 24 divided by 4 works out perfectly. But then if you add 1 more, you get 25. What about 26? Yeah, it's equal to 2 mod 4. The modular, is basically reducing the number as far as it can go. Again, there are 2 ways of looking at it. There are 2 ways of looking at modular arithmetic. You could look at it as, I'll put this in a different color actually. Here we go. You could look at it as 26 divided by 4 is equal to 6 remainder 2. And that 2 is the number that we're looking for. Or you could look at it as 26 minus 4 minus 4 minus, I know it is too much. That's why I'm talking about the remainders. Minus 4 minus 4 minus 4 minus 4, and that's as far as I can go. But it works. I know. It's just 2 ways of kind of looking at the same problem. The reason why modular arithmetic becomes so vital is because of its cyclic nature. What do I mean by cyclic or cyclical? Or cyclical. What do you think? What does it mean? Yeah. Repeating over and over and over and over. So if I were to go through this, and I did 27 mod 4, I'm in modular 4. That would be what, 3? What would be 28? Because again, what it equals is the remainder. Exactly. Well, no. Don't say no remainder. You're saying it doesn't exist. It does exist. It's the number 0. And then after 28, well, 29 is what mod 4? 1. Cyclical nature. And then it goes around again and again and again and again. It's similar to a system of binary. When you think of binary, what are the only numbers in binary? 1 and 0. What about trinary? No, not to 3. 0, 1, and 2. Yeah. I know, it's kind of weird like that. In mod 4, it's kind of like, now I'm going to say this word even though I don't think this word exists. In mod 4, it's like quadnary. Okay, quadnary, quad implying 4, but then the numbers that are included are, watch me now, 0, 1, 2, and 3. Yeah. Again, I don't know if that word exists. Yeah. Well, tertiary does still sound like 3. I know. Wow. Woo. I know, right? It's like I just take like a broomstick and swing it upside your head. You'd be like, April Fools. Yeah, exactly. Anyway. Now, again, the reason why this is very helpful with this kind of cyclical nature may not be obvious at the moment, but let me show you something a little bit more using this modular arithmetic. Get my little paper here. I'm going to do, let me think. Give me a single digit number.
7.
Okay, I'll do 7. I'll do 7.
That's pretty nice. Pretty
Quatern. It might be. Sky says it might be quaternary. Quaternary. It might be. I don't know. Anyway. So now check this out. 7 to the first power. Actually, you know what? No, I'll do to the 0 power. 7 to the 0 power is equal to 1, which is the equivalent of 1 mod 11. I know it sounds silly to put that, but it's kind of like a basic case. Yeah, 7 to the 0 power. 7 to the first power is 7, which is the equivalent of 7 mod 11. Now, again, it's like, okay, why is this a big deal? Oh, good question. A couple ways of looking at it. But you could think of it like this, right? The number 1 divided by 11 is equal to 0 remainder 11. Remainder 1. No, yeah, remainder 1. What am I even thinking of? Because if you actually did the 1 divided by 11, you would get this weird kind of a decimal where the remainder would be 1. Like that. It's like, how many times does 11 go into 1? 0 times, multiply, there's your remainder at the bottom. Well, to get the decimal, but I don't want the decimal, I just wanted the remainder. Yeah, I just wanted the remainder. Same thing with 7, but now here's where the more interesting thing comes into play. The next one I'm going to do is 7 squared, which is obviously 49. Divided by 11 gives you a remainder of what? I'll show you. I'll show you. I'll show you on the calculator. Hold on. Zooming in, zooming in, zooming in, zooming in, zooming in, zooming in. Okay. 49 divided by 11 obviously gives you this decimal, correct? I don't care about that decimal. I'm sorry, let me rephrase. I do care about that decimal, but I don't care about that whole number of 4. I care about the remainder, don't I? So I'm going to subtract that 4. I'm going to do a math enter, enter in order to get the remainder. That's literally how you can do it.
Bro, that's kind of wacky.
Isn't it?
Yeah.
But it's the simplest way of doing it. It really, really is the simplest way. Watch, I'll do it again for the next one. 7 cubed. Now, 7 cubed, for the sake of argument, is the number 343.
Marky out of his 7 times table down flat.
Anyway. But what is the equivalent mod 11? Now, again, I'm going to go to my calculator. Let me zoom in. I got to figure out what 343 is mod 11. So I'm going to divide it by 11. I'm going to take off that whole number. Now look at math enter, enter. It's frac. The remainder is 2. Yeah. The remainder is 2 mod 11. Now, so far, I just want you to see this real quick. I'm going to go back one page, and then I'm going to come back to these 7s. Look what happens when we did mod 4. What's the deal with the remainders? They go in order. What's the deal with the remainders? They look pretty random. Now, when we did mod 4, what were the only types of remainders you could get? 1, 2, 3, and 0, right? But when you do mod 11, you can get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we continue this, these remainders will also follow a cyclical pattern, but now they'll be randomized.
I see now how the encryption works.
Well, no, you do not see how the encryption works.
I got it down.
But you do see some level of, oh, this might be useful for encryption. You know what I'm saying? Yeah. 7 to the 4th power. Now, again, I'm just going to do the calculator here. 7 to the 4th power is the number 2401. It is. At some point, I'm just going to stop writing the number, just so you know. I'm just going to do 7 to the power. But if I go to the calculator, and I take that number and I divide it by 11, I get rid of the whole number. I do a math enter, enter. Oh, no. Yeah, at some point the calculator gives up. At some point the calculator kind of gives up because this thing is so large. But, remember before it gave you the fraction 2 over 11 and 5 over 11 and technically 7 over 11, right? I found my remainder. Hold on. I'll do one more 7 to the 5th, and I'll show you how this works, okay? So, again, I left a blank there, so left a blank right there. And I'll come up to the board just to show you how this works. It's like a lot of number manipulations, it's really messed up. But basically, I'm going to take this 16807 number, and I'm going to divide it by 11. Now, the calculator is going to give me some crazy decimal. And we're going to lop off the whole number, correct? Yeah. So if I take that number and I divide it by 11, it gives me 1527.90. Well, technically it's repeating. 90 repeating like that. I'm going to lop off the 1527, and the calculator is not really going to help me get the answer. Or it is going to help me, but it's not going to give me the fraction. But you got to know that that fraction is something over 11. It's something over 11. So if I were to take that minus the 1527, multiply it by 11, it spits out 10. Yeah. That's how this thing would go. Now, again, there is a cyclical nature to this. I'm going to actually knock out the rest of the page in a moment just so you can have it. And we can see exactly. So far we got 1, 7, 5, 2, 3, 10. Interesting. Now, I'm not going to write out the full number here, but I am going to give you what the rest of these mods are. 7 to the 6, 7 to the 7, 7 to the 8, 7 to the 9, 7 to the 10. Actually, I'll show you 7 to the 11 as well. We'll see what that is in a moment. I think the calculator at some point is going to give me scientific notation, which is not going to be pretty. You learn scientific notation? Okay. So I'm going to do 7 to the 6th power. I'll zoom in here. Focus that. 7 to the 6th power divided by 11. Lop off the whole number. Multiply that by 11. Rounding error, but it's 4. 4 mod 11. I'm going to do the same thing for 7 to the 7th power. I'm going to divide that by 11. I'm going to lop off the whole number. I'm going to multiply that by 11. Again, rounding error, that's still 6. 6 mod 11. Now, there are computer programs that will automatically calculate modular arithmetic. Anybody taking any form of computer programming with Sellers? You are? Have you learned Java at all? Okay. Are you gonna? Okay. In Java, there actually is a dedicated modular function. It's really nice, actually. Oh, yeah. Yeah, absolutely. So zooming in. Again, this calculator has limited capability. See how far I can go with this. So far. Divided by 11, lop off the whole number, multiply that by 11. That's a 9. I'll show you the full list in a little bit.
I'm not gonna lie, for how expensive these calculators are, I think they should be able to go up to mod 3000.
Well, you know the interesting thing about this calculator? I think I may have said this before. This calculator has more computing power than the Apollo 11 space mission. Yeah. Insane. Divide that by 11, lop off the whole number, multiply that by 11. That's about 8. Let's see if this thing, I don't know if this thing can do it. 7 to the 10th power. Holy crap. Divide that by 11, lop off the whole number, times 11. What is that equivalent to? Yeah, just 1. Interesting. Did we hit all of them?
I believe so. Yeah. No. Yes. All the way around. We hit there.
Yeah, I don't think we hit 0. Did we hit 0?
Zero option.
0 should be an option. Hold on.
No, we only get 10. We have 10. We have 1 through 10.
We have 1 through 10?
Yeah. That's 10.
Interesting. Yeah.
So speaking of philosophers with their enigmatic person, did you know that Plato, his name was his wrestling name, and it means wide.
Was what?
Plato's name was just wide in Greek.
Okay. There was a wrestler called the question mark. Anyway, back to this. Part of the reason why we can't get 0, though, is because the number would have to be divisible by 11. The number would have to be divisible by 11 exactly. And none are. They're only divisible by 7. Right? But you can still see that cyclical nature, though. We got back all the way around to 1. We got 1 through 10. I wonder how this could potentially be helpful with encrypting things. Now, obviously, I've talked a little bit about public and private key, but I'm getting away from that for a moment. If I had the numbers 1 through 10, and I wanted to find some kind of a unique way of listing out those numbers, this is a unique way of doing that. Fair? Yeah. Pick the number 7 all the way through. The fact that 11 is prime is helpful. The fact that 11 is prime. And the fact that 11 and 7 are what they call relatively prime. They have no common factors. It's kind of weird. How many letters are there in the alphabet?
26.
Huh. It would be interesting if we could find like a unique way using modular arithmetic to rearrange those numbers. Huh. Almost like if we had like a mod 27 almost, you know? If we had a mod 27, we could probably figure out like 26 unique ways of listing that thing, you know? I'm not actually going to do that. I'm just kind of showing you how this works. No, I'm not actually going to do that. I wanted to do something that was a bit more manageable right here. But yeah, I love this thing. Modular arithmetic. Like I said, there's a lot of theorems that go around with it, but this whole thing is cyclical. This whole thing is cyclical. When we eventually come back from break, I am going to go into some more details with modular arithmetic. I'm going to get some practice with it. We're going to be able to do some computations with it. You're going to be able to visualize it. Because there are ways of visualizing modular arithmetic. But I want you to think about it. Like, it just hit 9 o'clock, right? 9 o'clock plus 4 hours. 9 plus 4 is 13, which is equal to 1 mod 12. Just, yeah.
IQ. This class got me like really question.
As it should be. As it should be. Well, time is a construct that is based on the system that we have going around the planet, you know? Think of it this way. We count in a decimal system. Fair?
Yes.
We count in a decimal system. Why a decimal system?
That's how the government said it.
No.
Isn't like some of that's how math all work out.
No. There's more than just decimal systems. There's binary systems. There's base 60 systems.
Know what that means?
Well, think of it this way. How many minutes are in an hour?
60.
Ooh, base 60.
Oh,
Dang
that
it.
makes-
And then after you hit 60, it begins repeating.
It's all a mod.
Everything's
Everything's a mod.
Yeah. Do you know why 10 is the most basic way of doing, or the decimal 10 system is the most basic way of doing numbers today?
Because
No. You have 10 fingers.
Oh.
you love it?
Here, I'll show you one more trick. You ready? You probably already know how to do this. Do you know how to multiply 9 on your hands? Okay, you ready for this? Okay, some of you might know this trick. Okay? Look at my hands right here. 9 times something.
6.
9 times 6. Now 9 times 6 is what? 54. 1, 2, 3, 4, 5, 6. 54.
Oh, that is so cool.
Give me another one.
9 times 8.
9 times 8. 1, 2, 3, 4, 5, 6, 7, 8. 72.
What about 24, huh? Boom. Boom. What's that one?
9 times 24, that would be 180, 100 and, oh, you said 24?
Yeah.
Okay. That would be 180 plus 36. So that'd be 186, 216? Dude,
Yo, what's 9 to the 24?
right.
I do.
No, listen. You said 9 times 24, right? You said 9 times 24?
Yes.
This is what I did in my head, okay? Instead of 9 times 24, this is what I do in my head.
Josh is like, what's 9 times 24?
Dude, I learned that from my dad when I was a kid. Well, my dad knows how to do math in his head. Just saying. My dad is the type of guy that could, watch my Little League games or when I go bowling in a league or something like that, and he can actually figure out these averages in his head in a matter of moments without thinking about it. He's got a mind for it.
He's like, yo, that picture doesn't
Kind of.
You see that?
Yeah. Anyway, so we have approximately 10 minutes to go. I wanted to show you just what I did on that website, just to kind of take it a little bit farther. What is? Yeah, real quick. Right. So we got here, and you said that you found out decade.
Yeah.
How did you find out decade?
So, go to Pixlr.
Pixlr. Hold on. Pixlr. Okay.
Now, go to the left one.
Mrs. Hopkinson from Guidance, call the main office. Mrs. Hopkinson, call the main office.
What?
Open up the thing that's already there. Now, copy the image into that.
Copy image. Paste.
Now, go to the drawing tool.
Where is the drawing tool?
Click around to paint in that.
Paint?
Yep, and scroll down. Click on the colors. So, click on white.
Yeah.
Scroll down.
Ah.
And then they'll drop her thing.
Once I click here.
Ooh, you gotta hover over it with the dropper.
Oh, and how do I edit undo?
Control Z.
There we go. With the hopper, the dropper.
And then hover over the thing you want to actually, just all the answers, all the letters in answer. The black is the same black.
So what do I do?
You hover the letters.
Over the letters.
Over the letters. And then click on over the actual color of the answer.
What do you mean the actual color?
Click on A, the white of A.
Oh, on the white of A. How do I get to the white of A?
Just click on A.
Yeah.
Not the bubble. You do the plus.
Okay.
But with the dropper on.
Oh, with the plus right here.
Yes.
So I get C. Do it again. I get C.
I don't know what's happening now, but
This is what you told me to do.
I did, but I don't know what you're doing. I don't know how you're getting that.
Whatever, but you told me the answer was decade. I understand that it is, but
Is that? I think you're just on the border between the black and the white, so it's
all right.
mix the colors.
So anyway, I got here, right? And this one was actually pretty funny because I stared at this thing for the longest time, right? I right-click to look at the source code, It said no geography required. No geography required. Do you see it?
1009.
Yeah. I couldn't see it right at the computer screen until you kind of squint a little bit. It's kind of not burnt into the image, but it's in the background almost. 1009. But it's Rome. Look at the top left of the screen right here. Numerals. What'd you find? Ah. Oh, for which one? Oh, right here? Oh, well, the thing is, it's like numerals, right? So I found out that 1009 in numerals is MIX. Oh, hold on. All right, I already got to click. So why is it clicking like that? There it is, mix.
No, it's 11.
Yeah. So then I got here with keys. And it's like the keys to solving the level are right in front of you. And then it says I to O and X to E. I'm sorry, X to C. And then it says to decode this.
I got another thingy. I forgot what it's called though.
U, B, C, W, B, R, U, I, B. The keys to solving the level are right in front of you. Technically, right now, there are two types of keys in front of you on this level. There are two types of keys in front of you in this level. There are two types of keys. Nope. You have a set of keys in front of you, and you have a set of computer keys in front of you. No, gentlemen. You have a set of computer keys in front of you. Look at the key for I on your keyboard. What's directly to the right of it? And look at the key for W. What's directly to the right? Not W, X. What is directly to the right of X? The key is right in front of you. Tell me what's right in front of you. I'm sorry, what's right after you? What's right after B? Right after C?
I hate this website.
Right after W? B? Oh, I already got N. What about R? U? I? B. So if I change the word mix to invention, brings me here.
Yes.
And then I got stuck. View page source. Now, notice the title of the actual thing says Friday. And then it says 1949 first, 1984 second, 1946 second, 1955 first, 1937 first, 1981 third. We do have to go back in time. Pretty sure we do. 1949, Friday the 13th. Calendar date and time. So the first Friday the 13th was in May. So here, someone go to the board and write the word May. Catch. And then the next few you're going to write underneath of it, okay? So hold on. Let me go to the year 1984. It's true. And it does say the second one. The first one was in January, so it says the second one was in April. Write the word April underneath of it. Here, use this one. This might be better. Throw that one out.
Ah. I wasn't prepared.
What's the URL for this one?
Timeanddate.com.
No, the
Oh, this one right here.
yeah.
Invention. It's the cipher / pippity / invention.
What's the password?
Password.
I got a password thing.
Oh, did you not do the previous levels? Decade.
Bro, you just got messed up. Hey.
All right.
Why did I say
1946. The first one was. Where are we? September. And then 1955. The first. Wait. Yeah. Maybe. Hold on. Let me go back to 1946, actually. 1946. It said the second one. I apologize. Erase September and put December. And then after that, write May.
Me again?
Yeah. And then write August.
Is it November?
Yes, it is. And how would one know that?
Supposed to be
Madman. Yeah.
That's it.
So what do I do? Do I type? I'm going to change the word invention to madman, or do I have to do a?
That's what you do.
I need a thing here.
Is it
Try doing
Try
it
that.
again.
Nope.
Try. What did you put in?
Madman.
Right. How much is it?
You went to 14.
I went to 14.
Oh, I had to type in decade again.
Yeah.
I would say
it doesn't save right.
That's
I
weird,
think it
dude.
brings you back to the latest one you've done, but that applies to.
Gotcha. And then it says, what the? I can't hear you. Talk faster.
That's the speaker.
I can't hear you. Talk faster. I don't know. Bell's going to ring. We'll have to figure this out another time.
Yo, he called it. It's almost like he saw time.
Oh,
Time is an illusion.
there was a bunch of gibberish.
Anyway, if you haven't left a comment in the chat, please make sure that you do so. I already see the 3 of you guys who left a comment there. Thank you for that. And I will see you guys next time.
Look at that, guys. Time is up. Everything is possible.
Time is an illusion.
Bro, this class is gonna be great with 85 minutes.